I would like to start off with this aerial picture of the Netherlands. It's not far away from here, and it nicely shows the amount of agricultural activity that we have in this country. And to feed all these fields, we use a lot of artificial fertilizers. We import a lot of nutrients. And the nutrients that we excrete as humans are largely wasted in our treatment facilities. And I think that's a shame because, as you can see, roughly 25 to 60% of these nutrients can replace the artificial fertilizer usage in the Netherlands. And as you might know, fertilizers are becoming very scarce. So we should do something with this, stream. So my name is Marinus J Moerland. I'm a PhD candidate at Wageningen University. And I've been working on safe nutrient recovery from concentrated black water for the past 4 years. So we're really getting into dirty wastewater treatment now instead of the drinking water that we had before. Concentrated black water is the toilet fraction of domestic wastewater. And I work in this project in under the scope of the Run for Life project, which is an European project, in which we look at the domestic waste water stream as a whole and try to recover all the resources that are in there. For instance, the gray water we can recover and use as irrigation water. And the black water, so the toilet water, we can treat biologically to produce fertilizers that we can reuse in agriculture. And this whole project revolves around source separation or new sanitation. And if we look at our wastewater treatment process, currently, especially in the Netherlands, all the streams are collected in one big stream, transported to a centralized wastewater treatment plant, where nutrients are removed, not recovered, but usually removed, and these effluent is discharged onto surface waters. So new sanitation is a different concept where we separately collect all the different waste streams. So like I said, the bathroom water or the rainwater we can treat and reuse, for instance, as irrigation water. And the black water, so the toilet fraction, we collect separately, and we treat them decentralized. So for instance, this picture is from Sneek in the north of the Netherlands, where DESA runs a source-separated community area, and they treat the toilet water locally. And the nutrients that we can recover can then be reused as a fertilizer. However, there are some problems, and they mainly revolve around pathogens and micropollutants, so pharmaceuticals that we use. They are also present in our black water because we excrete them. And of course, we don't want to introduce them to our food chain. So that's the main challenge, to remove those pollutants. And we use anaerobic digestion. So the organic matter is then converted to methane by a biological process. And the nutrients are mineralized so that they become available for recovery. And this process has already been demonstrated at mesophilic conditions, so 35, 25 degrees Celsius, and has good process performance. However, to remove those pollutants, we want to go to thermophilic or even hyper-thermophilic, so 50 to 70 degrees Celsius, to ensure pathogen removal in one step and produce these hygienized fertilizers. So the main challenges of my research were to optimize this process at these high temperatures to ensure good process performance, mainly in the form of methane production, to ensure pathogen removal, of course, and to give an outlook to how to recover those nutrients. I operated 3 reactors of about 5 liters, retention time of about 5 to 7 days, and they were inoculated with thermophilic sludge. We fed them with black water that we collect through vacuum toilets from our own department. And additionally, we operated a calcium dosing reactor where we dosed calcium and we applied nitrogen through a gas lift to enhance mixing to precipitate calcium phosphate. So if we look at the results, first of all, the first aim to produce the methane and the process performance, we see that on the left side is actually the influent organic distribution of the black water. And we see here in green the methane prediction. So at thermophilic conditions, we have about 60% methane prediction and high COD removal. So most of the COD is removed, most of the organic matter. At 70 degrees, we have much lower methane prediction and also lower organic matter removal due to the high temperatures. So the thermophilic reactor is actually better at producing methane than the hyper-thermophilic reactor. But what about the pathogens? Can we go to this lower temperature without compromising the quality of the effluent? We looked at pathogen removal, and we see here at 35 degrees, you have the reactor is snake. And in blue, there's the effluent pathogen indicator organisms concentration. And we actually see that at 35 degrees, that's quite a high fraction of the pathogens still present. Whereas we go to 55 or 70 degrees, there's almost no pathogens present, meaning that even at 55 degrees, we remove all the indicator organisms. Lastly, towards the nutrient recovery, I focus here on phosphorus in this slide. And we see in blue, the total phosphorus removal is about 70 to 80%. And there's not really much difference between the regular operation and the operation with the gas lift and the calcium dosing that I showed earlier. So the removal is already quite high, but it's not further enhanced. However, when we look at the sludge composition, so the solids composition in the reactor during the calcium dosing, we actually see that there is an increase in calcium content and phosphorus content inside a solid part of the reactor. So we do have some sort of calcium phosphate precipitation that we can observe. And if we look at the removals, so we recover 100%, a little bit more of all the phosphorus that we remove from the black water, we recover inside the solid fraction of the reactor. However, we still need to somehow get it out of the reactor. So, yeah, more or less in conclusion, thermophilic anaerobic digestion is a more suitable technology for treating concentrated black water. It outperforms hyper-thermophilic anaerobic digestion without compromising the pathogen removal. We also looked at micropollutants removal, and we're still publishing these results, but yeah, more or less the same is happening in that area. For the nutrient recovery potential, there is quite some nutrient recovery potential for phosphorus in the solids. I did not really go into nitrogen in this presentation, but since the temperature is already quite high, and we also have a gas flow, and the pH at these conditions is also quite high, we create very suitable conditions for ammonia stripping. So there is some potential for safe nutrient recovery from this black water stream. And that's what I wanted to share with you today. So thank you very much for your attention, and I would like to know if there are any questions.
Thank you very much. Questions? Many? There in the back. Oh, okay. Yeah, now you already had your turn. Eh? First the ladies.
Sorry.
Yeah, the dice.
I would first like to thank you for the presentation. It was very interesting. I have a question because you slightly or shortly mentioned micropollutant removal. Yep. Which classes are you focusing on in that specific paper? And are you also looking at classes that kind of vary in persistency and mobility?
Well, we focus mainly on pharmaceuticals because it's source separated, and personal care products and so on mainly end up in the bathroom water and not so much in the toilet waste. So we look at diclofenac, carbamazepine, metoprolol, those kind of substances. And we did test different classes in terms of resistance. So I'm not really a micropollutant expert, but I did in collaboration. But for instance, diclofenac and carbamazepine are usually very known to be very resilient against removal. This is also what we observed, but we, especially at the thermophilic conditions, did achieve quite high removal also for those compounds. Yeah.
Okay.
The rate is, I think for most compounds, is about 95% removal. For those that are mentioned, is about 50 to 70% removal.
Okay. There was another question over there. Yep. And then I come to you.
Hello, thank you for your presentation. I'm from France, and I'm working at Paris Sanitation Agency, and we are working on source separation. You didn't spoke about urine separation. There is a major stake on nitrogen, and so that is my question. Why?
Yeah, so your question is why not urine separation toilets, I mean?
Yeah.
Yeah, could also be possible. We do have those at our department. However, our experience was that they don't really work as good as they should. So the urine separation, I mean, for male toilets it's easy. You have a urinal and a regular toilet, but for female toilets it's quite difficult to separate the two streams. And I think that's the main issue with urine separation.
Okay.
Thank you.
Yeah. Okay. Then last question, Emil. Thank you. Short, eh?
Yeah, very short. Thank you very much for your nice presentation. I was interested in the techno-economical aspects of your system, more the system approach. On which level would you be able to cost-effectively approach this? Is it on a household level, or you mentioned something, an apartment block, or what is the boundaries for that?
Yeah, I think that's a very good question. The main benefit of these systems is to locally close nutrient loops. So locally treat the black water and reuse them in a close proximity to the community. And there are some nice examples in the Netherlands. By Dessa, as I told you, they are also on the Aquatech, I believe. So you can always visit them later. They have a community area in...
Yeah.
Sorry?
No publicity, no.
No. I don't work for them, but they have a community area with I think one with 32 households and the other one with 200 households. So relatively small areas where they apply this source separation and treatment. So I think that would be the size that we're looking at. So the relatively small community areas.
But you did not do the calculations?
No.
Okay. Thank you very much.